Right, okay, number representation. Remember, the key thing is keywords. Using the correct terms. Don't say numbers or numbers with pluses and numbers with minuses. Alright, because that's nonsense. So we call them unsigned, oops, get my pen on, unsigned, which are wholly positive. So 0 and up. So if we're talking about 8 bits, that's going to be 255. And remember, the other thing that you're going to be expected is that you can say how many different values can you represent. And please always remember 0 as a value. That's the key thing that people screw, and they'll say, oh, with 8 bits you can do 255. And you go, well, actually no, it's 256 because there's 0. It's not what is the largest number. So the unsigned numbers are wholly positive, but you don't get many uses of numbers like that. So we have signed numbers. So these are negative and positive numbers. Okay. Unfortunately, loads of different formats. So in a signed format, we have got sign of magnitude, which is the human form, just a duplicate of that. And we have got 2's comp, which is the computer's way of doing it, which looks a bit alien, but works with arithmetic. So when we're adding and subtracting, we have got a number, and the sign is just part of it. Okay? It's complementary with the number. With sign of magnitude, you've actually got 2 pieces of data. And when we're processing data, we don't like multiple pieces of data in one thing. When we look at the database section, you'll see that that is a thing as well when we look at database and data storage. Okay, so the first thing is just ranges of values. So you might get asked to do 5 bits, unsigned, what's the range of values? So what's the lowest value going to be? The smallest magnitude? 0. What's the highest? Right, remember there's a dumbass, remember no calculator, so we can't use like 2n minus 1 and all that. So we do the dumb method. We go 5 bits. 1, 2, 4, 8, 16. And then what we do is we go, right, the next one, that's my range. Okay, so it's 32. All we got to do to work out what the largest value is there for is to say, well, 32 minus 1. Haven't we? And we say, okay, so the range will be 31. So no one's going to laugh at you if you've had to write down column headings to work it out. Okay? It's the sort of thing that I would make a mess. It's one of those things that's so simple that you are going to cock it up. You're asking for it every single time. So they will ask that. They'll expect you to know the common ones. So with 8 bits, like we said, it's 0 to 255. When it comes to signed numbers, slightly different. So if I was to say 5 bits unsigned, what's your 5 bits signed, what question should you immediately ask? If you get a question like that, what should you be asking straight away?
Using sign of magnitude or 2.
Yeah. What method? So we need to know the method. So if we were to say S&M, sign of magnitude, you can do this a couple of different ways. So I'm going 5 bits. So I'm going to put 5 bits down. Now, what's the thing that happens when we're doing signed numbers? What do we get?
The most significant bit is like represents plus or minus.
Yeah. So the most significant bit is also used as a sign bit. So it represents whether it's positive, negative. So if it's positive, we put a 0, and then we just write the magnitude. So it literally is an interpretation of the term sign of magnitude. So you put a sign, and then this bit, the remaining bits are used for the magnitude. So again, it's easy to work out what the biggest is because you're saying, well, it must be this number here minus 1. Because remember, when we add all those together, that will always be 1 less than the next column. So if you add those together, you get 15, don't you? Okay? So again, if in doubt, and it comes up in the floating point stuff as well, what is the largest negative number, what's the smallest number and all that, they can ask you lots of different questions for that. You don't need to know what the number is, you can actually just write it in binary. So if they said in binary what's the largest sign of magnitude 5-bit number, you could just put 0, 1, 1, 1, 1. What would be the largest negative number
Minus 16.
in sign of magnitude?
Negative.
Oh,
It is just that bit flipped, isn't it? So it's the same magnitude. So as a negative one, you'd say 1, 1, 1, 1, 1. And we go, oh, that's minus 15. If I was doing it in 2's complement, so if I'll do the same, 5 bits, 2C, they shouldn't need to say times 2 complement. So in that, for the positive, the largest positive number, what do we put?
16.
No.
Oh no, 13.
It's got to have a sign of 0, hasn't it, again? So remember, this is the key thing with when you're doing the signed numbers, always start with sign. And you go, right, I'm going to put some column editing because I'm a dumbo. So I've got 5 bits. But the column headings are sort of irrelevant. So I say if I've got a positive number, I'm going to say, right, well, positive, I have to think sign first, put my sign in. Then I just say, right, well, using the rest of it, what's the biggest number I've got? And it's, again, plus 15. But with negative, it's slightly different. Because we know, unless we're not clever, unless we know what the system is, we can't write a negative number down. So what we do is we actually perform 2's complement, don't we? So we write down the positive version. And remember, this is where students really mess it up. They'll read 2's complement in the question and they'll go, oh, I've got to do 2's complement. No, no, no. You only do 2's complement when you've got negative values to deal with. So if you've got a pattern of bits and it starts with the most significant bit 1, you know you've got a negative number and you go, oh, bugger, I don't know what that is. Do 2's complement and find out what the positive version is. Remember, 2's complement is equivalent of like multiplying by -1. What's really nice about that is CPUs have basically got an instruction usually on most CPUs to do 2's complement. So if you want to like flip the sign of a number, you can just go bang, one instruction, really quick. Okay, so it isn't like what we do. We have to like do it all manually. That's got hardware to do it. Right, so if I want to know what the negative maximum is, I'll do 2's complement. So remember that involves flipping all the bits and adding one. But we've got a short way of doing that. We flip the bits until we get to the last one, don't we? So we go 1, flip, flip, flip. We get to the last one. Hang on, that's gone horribly wrong. I'm going mad. Oh, no. Right, so if we get to the last one, we put it as a 1. So that is minus 15. But it's not the smallest negative number, is it? What's the smallest negative number?
Negative 16.
Negative 16. Now let's prove why that is in a sec. But this is the reason why you can't necessarily write negative numbers down straight away. Because unless you know what the system... I'm not going to tell you what the system is. Alright? I know what the system is, but I'm not going to tell you. It's up to you. You will see like explanations of how to do it. But yeah, that's minus 15. You wouldn't necessarily think that that was minus 15 just looking at it. Okay, but if we was to do the 2's complement on it and flip it back, then we would. Now we said it's minus 16. So what would minus 16 look like? So well, you can't even write it, can you? But it actually looks like this. That's minus 16. But let's prove what it is. We do 2's, it's a negative number we can see. We look at the sign bit. It's always about examining the sign bit. And we say, oh, negative. I can't read it. I know it's negative, that's all I can tell you about it. So I'm going to do 2's complement. So I'm going to go flip, but the flip process, let's do it the long way first. Let's just go flip, 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 flip. So that was the flip. But then let's add 1. And the way that we add 1, this would be 1. This is why we do the quick way of doing it, but I just want to show you it. Right, so we go 1 and 1, and we go, no, carry 1. I know what's going to happen here. 1 and 1 and no is no, carry 1. 1 note and 1 is no, not 1. See, I've got ones and notes, and you go mad in binary. You're just like, right, everything's a 1 or a note, 1, note, 1. And that's how it's easy to mess up. Don't like it. I don't know what they're testing, to be honest, but that's what they're testing. 1 note 1 is no, carry 1, and then we end up with note, note 1, so we end up with a 1. So it actually looks like what we originally started with, which is a negative number, but we're saying that's 16. Why do we have that extra range? Because the range on the sign of magnitude is plus and minus the same number. Why do we get an extra value on 2's complement? Nobody? We're all done in the exam.
Isn't it because...
Go on, prove me right that you are intelligent.
2's complement, the most significant bit represents a number as well, just the negative version. Whereas in sign of magnitude, it's just plus or minus.
Yeah. That's the essence of it. We can explain that we can show it physically in a different way. But yeah, so 2's complement, the number and the sign all merge together. Okay? So it's integral. But with sign of magnitude, when we're writing a number, let's just do a 3-bit number. So this is plus 3. This is minus 3. So they're separate bits, but we have this anomaly because of this, which you just don't get in 2's complement. That is 0. What number is that?
-0.
Yeah, which doesn't even make sense. That's minus 0. So and you can see that pattern is the one that ends up being used for 2's complement. It's not like penciled in. You go, oh, we'll just use that pattern. No, the way that 2's complement works, the integral nature of it, like Tilly said, just gives us that extra representation. Okay, which actually does cause loads of problems, but it's actually quite useful as well. Okay, so that's the essence. You will get asked to talk about number ranges. You will get asked to talk about minimum values, maximum values. Right, let's talk about arithmetic then. So if you get a number in sign of magnitude and you're asked to add them up, then you've actually got to take the signs away. So if I add 5 plus minus 6, and I'm holding those numbers in sign of magnitude, so I would have 0, let's just do it as a 4-bit number. So I've got 0, 1, 0, 1, so that's going to be plus 5, and I want to add it to minus 6, so I'd end up with that. You can't actually just do that. It doesn't work. You've got to mess about with it first. Okay? Because it wouldn't make sense. If I just added that up, what should the answer be? Minus 1, shouldn't it?
Mm-hmm.
So we would expect the answer for that to be 1, 0, 0, 1. Won't we? Right, so if we just add these together, so we get 1, 1, no, carry 1, no, carry 1. It doesn't give you the right answer. It doesn't work. So in order to actually process that, you've got to actually examine the sign bits, decide whether you're actually subtracting or adding. So it actually means subtract 6 from 5. So sign of magnitude is no good for this. You can do it, but it requires extra processing. But if we write them in 2's complement, we can actually just say, right, I don't need to even look at the sign. I'm just going to add the two things together. So if I do 5 plus minus 6, so 5 is the same, plus 5 is the same in 2's complement. So that's plus 5 2's complement. But minus 6 I can't write down. So, and this is what you mustn't do. You mustn't do this on your exam paper. You mustn't go, right, I'm just going to write minus 6 down here. So I'm going to write 6, and then I'm going to do flip and add. So I'm going to go flip, flip. Oh, that's the last one. Keep it the same. Right, so that's minus 6. That was plus 6. If you're going to do this, show you're working out, say working. Alright, so I have got that, but I just don't just leave things sprayed across a page with no annotation. It is so important. The number of times I see students work, and you think, especially on the binary ones, where, let's say, I'll come back to that in a sec. You've got your area that you're working, question was here, and you've got like your lines, and you see some binary numbers here, then you see some binary numbers up here, and then someone does something down here, and then they go back over here, and they go here, and they go, obviously that's the answer. It's there, that's the answer. But they don't label it. You mustn't do that. You've got to try and work neat. Okay? So please don't do that, because that will make you come a cropper. Right, so going back, so I've got my +5, I've now worked out what -6 is. So when I put them together and add them, it should magically just work. But it's not magic. So I get 1 and 0. 1 and 0 is 1. 0 and 1 is 1. 0 and 1 is 1. And 0 and 1 is 1. And we know, because that is the number we can read in 2's complement, all the ones is -1. So it worked. 5 plus -6. It just works. You might need to reform. If you've got 5 -6, you might need to rework it. Just do a bit of algebraic changing and say, oh yeah, that's 5 plus -6. What it actually means is you do not need to do subtraction if you're using 2's complement, because actually what you do is you just take the second value and you 2's complement it and add. So you just say, no, take the second bit, times it by -1, add it on. So you don't actually need subtraction. So you don't actually need to build any hardware on your CPU in the arithmetic and logic unit to perform a subtraction operation either. If in the exam they give you 5 -6 and say write these in binary and then perform subtraction, don't do it. You can do subtraction, but I hate it. I don't like normal subtraction, but subtraction in binary is horrible because you have to like borrow from like 5 miles away. So always do 2's complement add. They have to accept it as the answer because that's how it works. Okay, right. The reason the 2's complement stuff is important is because of floating point. Probably your favourite. Floating point should be, and remember this isn't really floating point, this is OCR floating point. Floating point is not like this at all. So this is floating point OCR, where we have, and again, keywords, mantissa and exponent. So the mantissa is the DL. That's the detail of the number. What does the number represent? And this is the size of the number. Okay? How they express it in the exam is entirely up to them. They've never not used 2's complement, but they could turn around to you, so be warned, they could say, oh, the exponent is held in sign of magnitude. But they shouldn't do that, but they might do. They'll tell you how many bits. In reality, single precision floating point is 32 bits, but because 32 bits is a lot of bits, and you will screw that up, that's why they make this thing up. Okay? So they'll always have to tell you, I think, in fact, actually, there has been one question where they didn't do this. They'll generally always tell you how many bits for the mantissa and how many bits for the exponent. And they'll say they're in 2's complement. So you need to be careful. They'll never give you big sizes for anything. The only time they haven't ever done that is when they mention the word normalized. What does normalized mean?
It's when you remove all the unnecessary stuff. It's like 1, 0. And
You're on fire. She's right. Where we get rid of meaningless digits, effectively. So, but why do we normalise? To maximise what?
Space efficiency, I guess. So like you're storing the least amount of bits.
Think a bit more abstract. Now you're still going to use the same. All the thing with these formats, you will use a certain number of bits. You can't like say I'm only going to use 3 bits for this, because you're talking about in general, a general format. No. Maximize precision. Maximize precision. Because we've got a limited number of bits, if we're recording zeros or things that don't make any difference to anything, then that's wasted bits. All right? How can we see if a number's normalized?
If it is in the form 1 0 at the start, so it doesn't have a bunch of ones
Yeah.
leading up to it.
First 2 bits are different. Is the dumb way of saying it. So we have got, for a positive number, they should all start, and we're talking about the mantissa here. So we remember the binary point is implied. It isn't actually there. How are you going to represent the point? You're not going to store that. So it's implied that it's after the first bit. So that doesn't exist, but a number, if it's normalized, would always start positive, not 1. If it's negative, it's going to start obviously 1 because it's negative, but it's going to go 1 0. Which again, when you look at it, you think, oh, it doesn't make sense. Yeah, it's in 2's complement, so don't worry too much about it. So that's how you can spot it. So the only time they never ever said what the mantissa exponent was where they gave 4 numbers and they went, which one's normalized? And you had to like look at it. They were testing whether you knew what the hell that bit meant. The 1 and the 0 and the 0 and the 1. Okay. Right. So there's 2 tricks. They might ask you to add up floating point numbers, which is probably the hardest thing they can get you to do, but it's actually trivial, but it comes into everything else. So let's just go through the process. So one thing is being able to write decimal number in floating point. So decimal to floating point. So let's have a number. These will normally be simple numbers. But you've got no calculator, so they can't go represent pi in floating point or anything like that. It's always going to be some sort of power of 2 fraction. So let's go for 3.75. And then we need to decide what format. So let's go 5 mantissa bits, and let's go 3 exponent bits. So we've got we're using 8 bits, and we're deciding how we pack it. Okay? Right, so our first job is we look at the number and we say, is it positive or negative? Positive, isn't it? Right. We're going to write down a 0 to force it to be positive. So we've only got 5 bits. So let's do 1, 2, 4, 8, 16. Let's write 5 bits down. Well, let's just write down 3. So we got no. But we want to be able to put down 0.75. So just in the same way that as we go left, we double each time, as we go right, you can see 8 becomes 4, 4 becomes 2. So 1 becomes half. Then it's a quarter. Then it's a 8. Then it's a
16,
then it's a
32nd.
then it's a
64.
then it's a
128.
yeah, you're annoying me now. I thought he was going to say something stupid. I thought he was going to do a Pretty Patel and like do that. You know when she read them numbers at that time, she had to read like that 406,273 and she couldn't say it. It was like umpity tumpity tumpity bumpity 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 bumpity. It was like 3,000,065 of 29 million or something like that. It was disastrous. But anyway, right. You can put as many bits down as you want when you first start this, all right? I've just made sure I've got my positive in at the front. So I could have like put more bits, because I don't know. Right, so I want to do 7.5. So 7.5, and this is where you need your maths power. 1/2 and 1/4 make it 7.5, yeah? Right, so all the rest are zeros. So we write it down first. Then we need to normalize. So normalize means that we have one sign bit and then we go straight into detail. So where sign is positive, so currently the binary point is there, so this isn't normalized. Okay, because we've got sign bit, sign bit, sign bit. So basically what it is, we want to get rid of the duplicate sign bits because they're wasting columns that we want to use for detail. So we want the change to be there. That's where we want the binary point. So we do the shift, and this is important because this tells us what the exponent is. So we go move it 1, and I recommend you do this because they will want to see whether you got the initial place correct, and you might get a mark for that, and you're getting a mark for shifting it to the right place. So we've moved it 1, 2 positions, and that's where we put the binary point. So even though I've actually got, confusingly, 2 binary points written down, I've put the arrows on and I've shown that what I've got is a movement. Right, so the magnitude of the exponent is how many places I moved it. So the magnitude is 2, but is it negative or positive? Now, it's easy to work out because actually we've made that number smaller than what it originally was, haven't we? So if we just write that out again, so we only want 5 bits, we only have 5. So we've got the 0, then we've got the 1, 1, 1, 1. And we've got a number that is now less than 0, less than 1. So we've actually shrunk it, we've made it smaller. So to get the number back, we have got to make it bigger. So that means the exponent needs to enlarge it. So it needs to be a positive exponent. And we've said it's 2. So we can write our exponent down as that. If you get stuck in the exam, just think scientific notation or exponential notation or whatever you want to call it. If we've got a number 0.79 times 10 to the 10, that's bigger than that, isn't it? So positive means make it bigger. We've got a number that's smaller than what we're writing it down as. But if we put minus, we actually mean make it smaller, don't we?
Yep.
So when we've shrunk a number to normalize it, the exponent is always positive. If we have to go the other way, then it's going to be negative. So let's do one that does that. And then we'll go backwards and we'll do the floating point back to the, what's it? So let's have a number. So a number that is going to be a negative exponent is going to be something that is already less than half. So let's go for 0.125. Let's write that down. Now I'm testing your powers of maths.
It's an 8.
Alright, if you're going to get like that. Well, let's have...
Oh, that's going to be really bad now.
I was gonna do a 6125 or something like that, but no one. Right, 0.375. Right, that's 3/8. So let's put some column headings on. Now we know it's positive, but let's just go like one. I'm just gonna go 1, 2, 4, and whack in my positive sign, and then I'm gonna have to I'm gonna need to go.
1/2.
Do I need to go beyond an 1/8 to really? No. So I don't want to waste too much time doing it. So I know I've got no 2s, no 1s. I'm not going to get a half out of that. So it is just, yeah. What you can do, and what I have advised students to do before, is that wherever you start at, double up the numerator. So you can like say, oh well that's 2/8, that's 4/8. It depends how dumb you are. What system? I always work from the principle that most people are really dumb, and they want simple methods. Simple methods don't involve things that will really get complicated and cock up.
The simple methods are just better normally.
Yeah, they are. You know, overcomplicating something is that you're asking for something to like cause problems. Right, so we've got that, we need to normalise it again. So currently, so don't ever cock this bit up, make sure you put the initial binary point in the right place. Right, so the binary point, we've got loads of leading zeros there. So we need to go this way. So that's where the binary point needs to be. So we're going to go that way. And we're going to put... if I drew some eyes on there and some hair, it'd be a clown, wouldn't it? Yeah. Right, so we've moved it 1. So the magnitude of the exponent is 1. But let's just write down our number so that we can see. We've got 5 bits. We actually have only got 3 pieces of information. What do we put in the other 2?
0.
Yeah, zeros. So there's our mantissa. Now, so we've got magnitude of 1. So we actually, what number have we got there? If we just look at that row as a bit of fixed point binary, what number is that?
That'd be
0.75.
Yeah, 0.75. So it's bigger, isn't it? So it's too big, so we need to shrink it. So when we do our exponent, we go, right, we've got 3 bits, minus 1. Well, actually, we're experts at 2's complement, so we know minus 1 is meh. Okay? And that's it. Right, so nothing complicated so far. When everybody, like, throws the toys out the pram and, like, goes, do what? Or wait, what? Is when someone says, write down a negative number in floating point. And everyone, like, starts wetting themselves. For some unknown reason. And I've never understood why. So let's have a go at minus 1.25. Let's put some column endings down. Let's go 1, 2, I don't know how many I'm going to want, so I'm just going to whack a load in. Quarter, oh, oops, what have I done wrong? I forgot a whole. I'm stupid. Quarter. Pardon, Richard? Don't think the microphone picked that up? It's a good job they can't see me shaking my head. Because I am shaking my head, listeners. I'm rolling my eyes as well. Right, okay, so what's our first problem? It's negative! 2's complement, negative. Ah, but when you're doing integers, what do you do?
just take the furthest bit as a sign bit.
No.
The most significant bit is like negative. Is the negative number.
No. No, because I can't write it down like that. What was you going to say, Tilly?
Do it positive.
Yes. Tilly's shaming you all. As usual. Yeah, I'll write down plus 1.25 then. And then I'll do 2's complement on it. That's all we do. It doesn't affect the exponent at all. The exponent is just the same calculation. How many places did we move the point? So yeah, let's write down plus 125. So we put, which is what you were saying, Dara, though, we put a sign in, but we have to put that positive sign in because we're writing down a positive number. So we go, right, okay, well, I can probably do this, 1.25, none of them, I'll have one of them, none of them. So that, and again, whenever we're doing the 2's complement, make sure the examiner knows that you haven't got it wrong, you're in the process. So we're saying that is 1.25 plus. Then I just do 2's complement on it. And I'm not going magic, I'm not doing anything magic. I'm just doing the same thing. It's just a pattern of bits to me. The fact that there's a binary point there, I don't care about that. I'm just going to do 2's comp. So I'm going to go flip, flip, flip. I'm trying to be clever and do it quick, so I'll cock it up. Flip, flip. The very last one, keep as a 1. Everything else should then be a 0. If you don't find that everything else is a 0, then it wasn't the last one. All right? Right, so that is now minus 1.25. We've got to normalise it. So we look at again, this is identical to the one we had previous, but this time the sign bit's 1. So we've actually got multiple sign bits. We're getting rid of the sign extension effectively when we normalise. So I don't need that and I don't need that. They're irrelevant. I want it to go 1 because it's negative, no. So actually, I've got to move it that way. And it's going to end up there when I normalise. Okay, so I'm going to go now and write down my 5 mantissa bits. So one sine bit, 0.0110. That's my mantissa. Right, the magnitude of my... The magnitude of my exponent is 1 because I moved the binary point 1 position. But I have shrunk this number. So I need to make sure that when I unnormalise and get my original number back, I make it bigger. So that's going to be plus 1. The other thing I would say, which I haven't done on any of these, is I would just make it really super clear that that's the exponent and that's the mantissa. If they're being really niggly and picky, you mustn't write the binary point in your final answer. If they're being picky. But they could be picky, couldn't they? Right, so there isn't anything scary about the negative floating points. Right, the bit, I find that is harder than going backwards. Going from floating point to decimal representation. So let's have a look at that. So I'm going to write down this first. I'm going to use the same format, 5 mantissa, 3 exponent. Right, what can you tell me about that number? There's 2 pieces of information you can tell me about that number. Yes?
It's not normalised.
It's not normalised. So whoever wrote this is a fool. What else can you tell me?
The bit that the exponent is negative.
Right, the exponent's negative. What does that tell me about the actual value?
So it's smaller than it would be if you just put a point in.
Yeah, so it's going to be less than 1. It can't be bigger than 1 because we're going to shift that and make it smaller. Yeah. Right. It's not normalised, but that doesn't matter for the process. Normalisation is just making sure we maximise that precision. Doesn't mean we don't sometimes hold numbers that way for various reasons. So we're going to go through the process. So the first thing I do is I look at my sign bit and I go, oh yeah, it's positive. So no matter what I do later on, I can double check. So it's a positive number. I then look at the exponent. It's 2's complement. It's a negative number, but actually we know what this is going to be. So what's this exponent going to be?
Minus 4.
Yeah, minus 4. We'll prove it in a sec. So that's my first job. I want to know what overall that number is. It's a positive number. And these, if they said, without telling me what this number is, what is it, what can you say? They're the things that you can say. Okay? Right, so the exponent's negative, so it's going to get smaller. By what? How much are we going to be dividing that by? Because every time you shift, remember, you're dividing. $16. You divide it by 16. Remember, if you shift right, you divide by 2. So if you do that 4 times, it's going to be 2 times 2 times 2 times 2. Yeah. Right, so it's going to get smaller. So what I'm going to do is I'm going to put my binary point in. But if I'm going to make it smaller, that binary point has got to go that way, hasn't it? So I need to pad it with a load of leading zeros. Put as many as you want. I know the exponent's 4, so I'm only going to move it 4 places, but I'm just going to go crazy and just put loads in. Right, and then I'm going to move it. So I'm going to go 1, 2, 3, 4. Oh, you click the button on the pen. Oh, that went miles up there. Let's go down. Sorry, everybody who's, well, if you're still awake. Right, I'm back. There's a switch on my pen right near the end. Stupid thing. Right. Okay. So that's my number. Now, this is interesting. We've only got. We can work out what the number is, but actually we've only got 5 bits. That is my sign bit, isn't it? Naught. Then I've got the binary point, and I've only got 4 more bits. That's why we normalise. That was partly normalised, not fully normalised, but it had been moved around. So if we were only using 5 bits, when we unnormalise, we're effectively unnormalising the number so we can find out what it is. If we was to only still use 5 bits, we would lose anything that was smaller than 1. We'd lose the detail. It's gone. We're assuming we're representing it as 0. This is a real good example of floating point. This is the problem with floating point. You don't hold things precisely, and when you start using those numbers, because you have to add them together, we have to unnormalise and things like that, and mess about with the exponents. Once you start doing that, that's when you get accuracy problems. Remember, precision is about holding the data. Accuracy is about using the data. You get rounding errors are accuracy problems. It's probably one of the hardest things to try and explain if you get to say what is the difference between accuracy and precision. Precision is holding the data. Accuracy is using the data. Right. So, but obviously we're not, because we're unpacking this. Then we're going to keep going. So we've got 1, 2, 3, 4. We've got another 0. I used to set questions for my A-level lot, and I used to give them like 6-bit exponents and then make them massive negative numbers and then say, what's that number? And I used to get like daggers thrown at me for doing it, because now I want to know what that number is. I've got to go, right, well, I'm not going to bother. I know it's less than 1, so I'm going to go half, quarter, 8th, 16th, 32th, 64th, then I'm going to go 1 to 8th, and then I'm going to go 2, 5, 6. And again, this is if generally they won't ask you to write the answer in decimals, say what is the answer. Okay, so that you could leave it like that theoretically. But again, if you want to be able to add that up easy, that's when I do the thing. So I go, oh, well, that's a 2 and a 4. So actually that is 7, 2, 5, 6. That's what that number is. That's the power of the floating point. So in 8 bits, we've been able to represent quite a small number. But we can't go, I mean, that was the maximum negative number. Okay? Maximum negative. I cannot, so theoretically the smallest number I could actually write would be with that unnormalized, so it would be something like 0, 1 with that, so it would be 1, 2, 5, 6 would be the smallest positive number I can represent. What's the largest I can represent? What would I write? What would the floating point pattern be for the largest positive number in 5-bit mantissa, 3-bit exponent? What would the exponent be?
0, 1.
Don't start incrementing on me, Tilly. You're letting me down now. You're letting me down.
Yeah, it'd be 3, I think.
It'd be 3, wouldn't it? But you're going to keep going.
No, I meant like the start
Oh.
time. I was a bit confused because it's not 0 or 1. I'm not sure what else it could be.
Right. So the largest 3-bit exponent would be that. 3. What would we write for the mantissa, for the largest positive number?
0 and then 4 ones.
Yeah. So they have asked those sort of questions before. What about negative? Largest negative number?
1 million zeros.
Yeah. Just like it would be as an integer. And with the same exponent, obviously. Any other questions about floating point? Right. The only other thing, which I think is mean, making you add up floating point numbers. I don't know what they're testing. They ask you about normalisation. Get you to unnormalise a number, fine. But don't then make them add the integers together, because it's just integer arithmetic once you've unnormalised them. So if we've got two numbers, so arithmetic. So everything else that we did for integers is the same. All right, so if you've got to say, if you've got, I'm not going to do this one, but if you've got 1.75 minus 0.25, you can actually rewrite that as 1.75 plus minus 0.25. It's exactly the same process. So if you can do integer addition and subtraction, you can do floating point. Right, so let's do something that we know what the answer is going to be. So I'm going to do 1.5 plus 2.25. What's the answer going to be?
2.75.
Yeah. So the answer, this is why I always like the binary questions, because you actually know what the answer is. So if you've completely gone crazy, you can at least get 1 mark for the final answer. But that's why they always have show you working. So the first thing we've got to do is write those down. So I'm going to go and I'm going to write them down as 5 and 3. So 5 bits for the mantissa. So I'm going to do 1.5 first. So let me just put my number line in. 1, 2, 4, half. Right, I don't need to go below a quarter. Okay, so 1.5 would be a 0 because it's positive. 1 and then a half. So that's 1.5. 2.25, again it's positive, so I'm going to put 2 and then 2.5. I want to normalise them, so that's the key thing. So I'm going to have these normalised. So for this one, I've got 2 leading zeros. So I want to normalise it. I'm going over the top now. I'm going to normalise it to put the binary point there. So 1.5 normalised is going to be 0, 1, 1, 0, and then remember we pad with a 0. So that is 1.5 normalised. What would the exponent be?
0.1.
Yeah, positive 1. So that's 1.5. The other one, oops, he didn't register the control key there. Right, the other one, we need to move the binary point twice this time. So we need to move it there and there. We've got to have the sign bit. So when we write this one down, we've got 0, 1, 0, 0, 1. So if we had to move that another place, we'd have lost the fractional part. We'd have lost it. The precision was gone. What's the exponent this time?
0, 1, 0.
Yeah, 0, 1, 0, 2. So that is 2.25. Both of them normalised. So in general, in the exam, they're going to give you them normalised. And just to make it harder. And they'll say, add these two numbers together. You can't add them directly together. You've got to have the same exponent, because the binary points currently exist there, but they're not really there, are they? My feeling on this is you can do it several ways. You can skew them so they're in line with each other and then add them, or just unnormalise them completely and add them. Okay? It's up to, I don't care which method you do. So let's try and see if we can skew them. Let's try that method first. So we want to make both the exponents the same. See, I don't like this method. So this one is 1 bigger than that one. Yep. So actually we need to move the binary point back a bit, don't we? For that one, to make them the same. So if I was to do that, I would have 2 equivalent numbers. They both have an exponent of 1. So we want to make them that. So the first one doesn't need to change. So we're just going to write that one down now. And we're only bothered about the detail part, the mantissa. So that the first one is okay. This one, we're going to write it down. So always when you're doing this bit, put the binary point in place. So we know we've got a 1 and a 0. And then after the binary point, we've got a 0, a 0, and a 1. we've got a mismatch. It's up to you whether you just automatically deal with that in your head, but I tend to put the zeros in. Okay? Then, now that we've got the binary points balanced, we can add up. And it is just addition, just like we did. So that's 0, 1, 1, 1, binary point, 1, 0. If they want to know what the final answer is normalised, then okay, we'll normalise it then. So at the minute, we've got to remember that we've got an exponent of 1. And we're normalising it. We're going that way. We're making it another bigger. So our final answer would be 0.1, 1, 1, 1. What happens to this 0? Yeah, it's dropped, discarded. We've only got space for 5 bits. Please don't make that mistake. This one's got to get bigger, so it's going to be that. So that's one way of doing it. The other way is to unnormalise, so you end up with what we started with. But the key bit, as long as you line the binary points up, then it is just arithmetic. Same for the subtraction. Okay, let's just work it back to make sure we got the right answer. What did we say it was? 3? It should be 3.75, shouldn't it? Right, so whenever you're going back, we're right. We know it's a positive number, so we haven't got any messing about with 2's complement to worry about on the mantissa. We look at this and we go, right, it's plus 2. Plus 2 means make this bigger. So that means take the binary point that way. So we're going to go 1, 2. So my binary point goes there. As soon as I do that, I can put my column headings on. So I've got 1, 2, 4. We know it's positive. We've got half and we've got a quarter. So that's 3.75, which is what we worked it out as. Okay. Right, I'll stop recording there.